Okay, podcast is on. Here, let's bring this over here. Testing, okay. Man, what happened? Bad hair day, okay. And we now move into segment 3 of our 4-part summary of cognitive psychology. We've spent a lot of time covering memory, and I hope that you got something from it. The idea that memory is indeed a reconstructive process, and that it's not like a tape recorder. And this has huge implications for how we solve crimes, for what happens in the therapy office, for what happens in your life, or how you recognize things. It's not. In some ways, memory is itself an illusion of time. And so, speaking of illusions, we as humans have an amazing ability to form images. Some of us are better than others. And so when we talk about imagery, it's interesting because some of us have this ability to almost think in pictures. And others are more what I'll call propositional. You'll see why I'm using that term. You know, it's that classic relationship issue where, you know, one of you kind of drives based on this three-dimensional image in the head, like I'm going north, okay? Don't give me directions, I'm just going in that direction. And you fight bitterly with the person on your side who has a list of instructions saying, no, 3 miles this way, take a right, you know, go 3 blocks. It's more just a set of instructions. But at any rate, imagery is interesting, if not only because of the fact we fight so much about it. And so what is imagery? What's going on here? That's what we're going to be talking about today. Now, I recognize that my notes for this went up a little bit late. How many people actually have the notes or the slides in front of you? How many people don't? Okay, so recognizing that you don't, many of you don't, we'll take this slowly, and with any luck, the pictures will be good. If we're talking about imagery, we need good pictures. So let's start out with this. We have this capacity for imagery. I think this is kind of fun because these are I don't know if this is true or not, but these are supposedly people who look like they're dogs. And if you look through here, it's pretty funky. You know, which combo would you most or least want to hang out with? I think the dachshund lady really looks like they all look like they're dogs. And the question is this true or not? It's pretty funny. And so essentially, as this is happening, you know, you're using your ability to recognize faces, but you're using your ability to construct images and compare them. And so imagery, mental imagery, is its own fascinating cognitive topic. And again, it's fairly visual. Not everything in cognitive psychology is visual, but this is. And so as we go through this, I want to first of all talk about somebody named Roger Shepard, and then talk about why we study imagery. I want to talk about knowledge representation, analog and propositional, evidence for analog representation, and we're going to go through some classic studies. And then we're going to ask about, do we really have pictures in the head? So before, you know, I keep talking about the illusion. And so we talked about illusions in perception, you know, perceptions in opinion. And then we talked about memory and attention. You know, attention is its own illusion. But memory, the illusion that we somehow have this tape recording of things that happened in the past, and the fact that it really doesn't quite work that way. Well, mental imagery, I'm here to tell you, is another one of these examples where you think you have a picture in the head, and in some ways what happens resembles a picture in the head, but it's not exactly that. And so how we form images, the nature of these images, is the subject of this talk. And so let's start with Roger Shepard. This is a self-portrait of Roger Shepard, the artist. And Roger Shepard, the artist, he's a famous artist even. He's interested in imagery. And so what are some of the themes in his art? And so let's take a look at some of the themes in his art. Well, I think you've already seen this. These are Shepard's tables. And the tables, one looks like a wider table than the other one, which looks like a longer table. And I'm here to show you that, in fact, the tables themselves are identical. Ooh, okay. Now, he's also drawn this, which I've shown you before, I believe. And this is called Terra Subterraneo. and you have a big guy chasing a little guy, but he's used depth cues, and in reality, the little guy is the same size as the big guy. There you go. Pretty amazing. Thank you very much. Okay. And then we have this impossible wheel. And I'm here to tell you that you couldn't possibly put that on your car. You couldn't even build this. Because if you look at this, the axle is going in one direction, and the tire, the wheel part, is going in another direction. How many people see the impossibility of this? Who doesn't? And was willing to admit it. You're not a mental imagery type person. Yeah. You're the person with the map in hand, or the instructions in hand, turn left, turn right, and you get in an argument with all these people who see the world the other way. It's okay. It happens. But there's only one of you in here. There's only one image negative person here. It's all right. Some of you just aren't willing to admit it. And some of you have decided not to show up today. We've got about a third of a house here. Okay. This is another one, and it says, I stand corrected. So did you also have problems when I showed like the Shakira video and it's doing all that kind of funny imaging and stuff? Were you there for that? Right, so it was, you never saw it even. Oh, wow, okay. And how about the gorilla? Did you see the gorilla when it walked through?
Yeah, I saw that.
Okay, good. That's a different sort of capacity. So your attentional capacity is different than your imaging capacity. Okay. So anyway, this is I stand corrected, and this is, again, impossible. You couldn't drive through this. And so you've got an arch going one direction, and then the path through going another direction. So this is Roger Shepard making some fun kind of drawings. Now this is an elephant. This is what happens when recombinant DNA goes awry. You have an elephant here. If you look at the top, it looks fine. If you look at his feet, they look fine. But somehow the feet and the elephant don't go together. You notice that if you look at the spaces, so here's the elephant. We move down, There's one leg and there's the other leg, but wait, the feet aren't in the right place. And so he likes playing around with these cues. And again, if I just flashed this at you very quickly, you might not even see that there was something wrong with it. In fact, some of you probably look at it and say, well, I still don't see anything wrong with it. Imagery. These are kind of fun. These are tiles with faces on them. Now, if you have the tile here, it's a smiling face. You take this smiling face and you rotate it at 180 degrees, and you have now a frowning face. Same face, just upside down. And so you'd like to play with that. Oops. Now you have a drawing of a pretty young girl, and yet there's something wrong here. You don't want to invite her to your party. Well, you might. But what's wild is if you look at one half, it all looks fine. She's looking straight at you. If you look at the other half, she's looking off to the side. And so she's got half a mind looking at you and half a mind looking away. But how many people see that? Great. Awesome. Okay. So he likes playing around with your mind. Now this is kind of fun. Now, for those of you who are having issues with reversible figures, if you look at this, how many people see both images in this? And the rest of you can look at it for a while. So, just out of curiosity, what do you see? Wait, what do you see in the image? A face of a man or a woman? Ah, okay. So the white face. Good. And so it's sort of it's like shadows. Right. How many people see that? How many people don't? Some of you. Okay, so yeah, in other words, here's her eye, there's her other eye, there's her lips. But now, the other thing that's here that you haven't seen yet, some of you haven't seen yet, is there's the guy playing a saxophone. God, the big nose. You see it? Okay, so you can reverse this back and forth. So this is Shepard playing around with reversible figures. So he's, again, playing around with imagery. So this artist is having some fun. And he's also, now this same Shepard, the artist, has created what are called Shepard tones. And so I thought I'd play some Shepard tones for you. Now I want you to listen to this. And the thing about these Shepard tones is they can ascend or descend, but they can go there forever. In fact, I played you what was how many? You heard that tone I was playing at the beginning, but I'm going to play these again for you, just to melt your brains. Okay, so this is something I showed in my sensation and perception class. Now, what I want you to see. Now, I've already shown you the impossible figure here. This is by Escher, but I want you to listen to the tones now. So how many people heard the eternal staircase and eternal descent? So you could play that in an endless loop forever. By the way, I mean, if you go to a really boring party, you know, where everybody's really strung out, try this. You know, see how long it takes for people to start going crazy. I went to UC Berkeley, which was a fun place for this, and played this in a room, and people started getting really irritated. It was fun, let me tell you. Now, so these are Shepard's tones. He invented these, this amazing artist. And again, so it's sort of auditory imagery. The image is of going up or going down, but in fact it's going nowhere. So again, the illusion created by the tone. So you can actually have auditory imagery, and he played with it. Now there's Shepard's tones come in various flavors. Now there's something called a Risset tone, or a Risset tone. Risset, I think is how it's pronounced. And he took Shepard's approach and essentially took out the choppiness to it and created this. And again, this is an eternal, you could have this play forever. I listen to this and I get kind of depressed. Here we go. All right, stop. Good. So it's pretty wild, right? It's pretty crazy. It's the thing, it goes on forever. You feel like you're going down into the abyss, this music, this tone, and yet it's an illusion. You're not going anywhere, right? So it's this sort of auditory imagery. Now, in the modern era, you can actually get this all on your iPhone. You can get the ring pipe application, the ring pipe organ application. Let's see. Whoops, hang on. Turn up the volume here. There we go. You can even make tunes. Hours of fun. And you have the Risset tone also. I should have done this before the exam. Okay, so there you have it. That's Shepard's tones, famous, amazing tones. Now, Why am I talking about this particular artist other than the fact that he likes playing around with visual and auditory imagery? Well, I told you he's interested in imagery, and you can see the themes in his art. At first glance, each picture looks okay perceptually, but upon closer inspection, each contains unusual or impossible information. In fact, same with the tones. You think it's ascending or descending, and then you realize, wait, I'm not going anywhere. And this can be quite disturbing to some people. You got to see things like size constancy failures. In other words, things you saw the little guy and the big guy, the little guy running away from the big guy, but in fact they're the same size. And you got to see things like figure ground reversals. We've talked about those. But now, the last thing on the list is mental rotation. You saw those images of faces turned 180 degrees and going from smiling to frowning. And mental rotation is going to be interesting, as we'll see. Now, the reason I keep mentioning that he's interested in imagery, but he's also an enormously famous cognitive psychologist. He's a mathematical and evolutionary psychologist interested in cognition. And he actually won the National Medal of Science in 1995. He's at Stanford. And this famous study by Shepard and Metzler in 1971 was a remarkably cool and influential experiment. And so as we think about imagery, I want to show you this experiment that this artist, and actually more famous as a scientist, guy from Stanford came up with. So he's interested in imagery. So you might want to remember the name Shepard and all this. Now, this is his famous experiment that he did in a number of instances. But you look at these. Now imagine you have two sort of blocks in front of you. And you have to tell me, they're obviously rotated, but are they the same or different? How many people say they're the same and see that? Some people have to look a little bit longer. How many people say different? Different? Why are they different? Oh, okay. Forget the thinner part. I don't know why it looks thinner. I see what you're saying, but you see how one could be rotated a little bit like this, right? It could be rotated like about 10 degrees, and yeah, you get it, right? Yeah. So what's that? Right, a little bit. And yet, they're probably drawn pretty precisely, but right. So most of us can look at this. And by the way, when my dad, I have a father, and he's like the most. Oh, thank you. Yeah, I know. I was hatched. Oh my God. No, I do have a father. I admit it. No, but my father is absolutely horrible at this. I mean, he had a brain injury, and then he got worse at this. But he couldn't do these. He could not for the life of him do these. There are people out there who can't do this. But you get the basic idea. So now let's try this one. Are these the same or different? Can one be rotated to match the other? Now go ahead, take a look at it. See if you can rotate it in your mind's eye, one into the other. How many people say yes? They can be. Are you sure? How many people say no? How many people aren't sure? Okay, this is definitely a no. You can't. These are definitely different blocks. Because if I take this one, wait a minute, and I rotate it like that. Wait. Right, yeah, hang on. This is also a lesson here. You can't do it. Now go ahead, stare at it for a while and convince yourself that's true. Some of you won't be able to do it. But so there's another one. How about this one? Go ahead, look at that one. How many people say they're the same? How many people say they're different? How many aren't sure? Right. So you guys we've got our propositional thinkers singled out here. Yeah. So the point is, if you had this block in front of you, so it's kind of like this, you could rotate it like that, about 45 degrees, and they would be the same. And most of us can do this. And again, notice the individual differences. So you're mentally rotating this in your head. At least that's what it seems like. Now here's another example. So the question is now we can do this. This is a multiple choice question just to re-traumatize you after the exam. You've got a standard, and you have to tell me which of the 3 comparison shapes it is. So go ahead, take a look. Some of you are going to be faster at this than I am. It's torture, isn't it? All right. How many people think they know the answer? How many people are still working on it? Okay, keep looking at it. How many people find this just torture? Yeah. Well, so this is dealing with mental imagery. So the question is so one of the things that's interesting to notice is that some people are better at mental imagery than others, at least this type. And this should not be an IQ test. I mean, it's not. But what it's doing, well, we'll see why it's interesting scientifically. But, I mean, to me, one of the things that's fascinating is how people differ on this. How many people think A? How many people think B? How many people think C? What's that?
She thought C, but then she meant A.
Yeah, it's very definitely A. Because, what you have to do is you have to straighten it up. You have to straighten it up like this, and then rotate it. I feel like I should be doing like a salsa step here, right? Okay. All right. Okay, so now we'll do another one. It's so obvious. No, just kidding. Sorry. All right. How many people think A? How many? Oh my God. Okay. How many people think B? There we go. We got some imagers here. Good. How many people think C? Okay. Right. It's definitely B, because what you have to do is, let's see. You take it, you rotate it up like this, and it's pretty much in place. Okay. What's that? Interesting. So you're now using. I'm not sure how that's going to work, but you're counting. Yeah. So you're doing a non-imaging approach to it, where you're counting. Yeah. I mean, and it's interesting. So you're compensating. So you're not in your mind's eye. You don't feel like you're rotating at all. You're just counting, which is very interesting. And in fact, when people challenged, I'm not going to talk about the challenges, but when people challenged the theory of this, there was a model by Carpenter and Just. You don't have to know this. And somebody actually, I remember that I gave them this exam in graduate school, and people called it the Carpenter adjustment model, and it's not that. No, it's their names were Carpenter and Just, as a husband and wife couple, and they came up. They essentially thought everybody was doing what you're doing, but I think that's probably not how it's turned out. So mental rotation studies. You have to understand when they started doing this. This is in the age of behaviorism. People didn't want to talk about imagery. They didn't want evidence. They didn't want to think that people did anything other than follow a list of instructions. And so along came Shepard and Metzger. Shepard, this amazing scientist and artist, and one of his graduate students. And this is what they did. And so this is, you can look at these in a minute. But basically what happened is, imagine you're a subject in this study. You'd be presented with 2 objects and asked if the second was merely a rotation of the first. And so let's say if we look at the first one, is it merely a rotation of the first? That's a yes. I should be like having a contest here. We have a couple pieces of pizza left here. Okay, so how about the second one? Is the second one merely a rotation of the first? I love it. Yeah, the answer is no. Oh, wait. Yeah, wait. Yep. You peer, yeah, so, there we go. Yep, it works.
You can turn the other way.
Wait, okay.
Yeah.
Oh, no, it doesn't work. Wait.
Turn the right one up.
Yeah, it works. How many people say yes? How many people say no? Right, it's a yes. But it's complicated, right? You have to sort of mentally rotate this in your mind's eye. And some of us and you'll notice some of us don't have a capacity for it, and so we come up with other techniques. Okay, and then the last one, is it simply a rotation? How many people say no? How many people say yes? Good, okay. How many people are just too scared to say anything? Okay. Right. So you get the idea. So you've got to figure out whether something's rotated or not. So you respond yes or no, whether it's a rotation or something else. And then what Shepard and Metzler did was they measured the time it took to respond yes or no. And on the yes trials, what they found, this is what you can see here. These are called for picture plane pairs. In other words, you might have to rotate like this. Sorry, this is turning into a bad musical here, like that. Or there are depth pairs where you have to rotate maybe like that, in depth, in three-dimensional depth. But the point is for either type of stimulus, what you can see is the more degrees you have to rotate something, the longer it takes to do it. Right? Now probably for you this wouldn't work out because you're actually counting numbers, right? And this is the point that they made, was that what's really interesting and cool about this is, in fact, the more you actually would physically have to rotate the two to get them in the same position, the same thing happens to reaction time. It takes longer to rotate things that are rotated far away from each other, and it takes less time to rotate things that are close. So that very first thing that I showed you, most people can do in just an instant. Whereas if you have to rotate things a long distance, it takes longer. So this is degree or angle of rotation. If you have to rotate at 20 degrees, you can do that in less than 2 seconds. But if you have to rotate at 180 degrees, it usually takes you about 5 seconds. And it's a linear function. In other words, it's a straight line. The more degrees, the more reaction time. And this, it may seem simple to you now, but it rocked the world of cognitive psychology because, first of all, here was Shepard saying, look, the only way that this would happen is if people actually had a mental image in the head and were rotating it. And it can't just be sort of the strategy that you came up with, where you sort of are trying to come up with elements and line them up. It doesn't work so simply. And so representation, according to Shepard, seems to correspond in direct ways to the objects themselves. And that may seem simple now, but it was huge back in the day, because all of a sudden it meant, first of all, that imagery, there actually is this thing called imagery, this mental phenomenon called imagery. And secondly, all of a sudden, people were studying imagery scientifically. So all of a sudden we can have a science, a cognitive and perceptual science of imagery. We can study it using things like reaction time and accuracy. By the way, this is a Far Side cartoon. I like this. Daryl suspected someone had once again slipped him a spoon with the concave side reversed. Get it? Please say you get it. He could rotate the spoon 180 degrees and it wouldn't happen. He could use the spoon. Okay, never mind. Oh, man. Long day. Okay. So this is imagery. This is the world of imagery and the scientific, cognitive science of imagery. And by the way, there is in fact a cognitive neuroscience of imagery. You can look at this happening in the brain, and we'll get there. We will get to the cognitive neuroscience of imagery for those of you who are interested in the brain and what goes on consciously in the brain. So why study imagery? Ooh, pretty picture. Okay. It's intrinsically interesting. Many of us are drawn to beautiful images, whether we're drawn to art, the way people look, imagery, what we imagine for many of us, and not everybody. Some of us are more either propositional or I'm not saying concrete, but many of us find this world of image to be quite fascinating. It provides a glimpse into how cognitive psychology works, because all of a sudden we're studying this thing that's completely inferred. You and I may know that we form images, and some of us form very vivid images. But how do you study it? And cognitive psychology works in this particular case by doing things like reaction times. And so something that we once thought was not open to scientific testing, something like mental images, the behaviorists would get upset about the concept. All of a sudden, we have a door that opened to studying images scientifically. We're studying conscious perceptions, internal conscious perceptions, in a way that makes sense in terms of science. And it has implications for how knowledge is represented in our minds and brains. And I'll talk about why I say that. Which brings us to our next, and this is really important. And is this me? Is somebody writing me messages again? Let me make sure the podcast is going. That's the main thing. Good, we're copying. Okay. Okay, what's going on here? Wrong lecture. Okay, knowledge representation. So we've talked about, I've used the terms propositional and analog, and I'd like to now make clear what they mean. And you will probably be able to identify yourself as more one than the other. So this is a map, right? We've all, back in the day, before GPSs, and we actually would have these things printed out on paper. If you can imagine, you're driving along the road, you have to pull out this big sheet of paper and find where you are. Some of you, your grandparents probably actually used maps. And so here's your map. It's really obsolete technology, isn't it? But you'd look at this map, and on the one hand, you can make instructions from it. You know, okay, I'm going to go to Littleton, so I'm going to drive up the 91, take a right on the 302, and get off at the Littleton exit right after the 93. That's just a set of instructions. Or you can sit there, get in your car and say, okay, I'm on the 91, Littleton's over there. I just need to get on the freeways to get me there. I'll keep driving in that direction until I get there. These are different ways of representing the world. So, if we think about knowledge representation, most of us, regardless of our imaging capacity, can probably mentally walk through our apartment. So I can close my eyes, I can picture where I live, and I can walk in the front door, and I can, walk around all the boxes and sit down on the couch. I can walk through my apartment and do that. That's imaging. So it implies some sort of internal representation of the apartment. And so I can actually have you imagine your apartment. I can have you you have knowledge about the layout of things. Okay, I walk in, there's a window over here, kitchen's over there. So you can do things like manipulate it in your mind's eye. But representations don't need to be literally similar to the thing being represented. So on a road map, you have the color of major and minor highways. And of course, if you actually looked at those highways, I don't think that anybody drives down a red freeway. So in some ways, there's something that's not quite literal about this picture of the map. There's not a number 302 the size of a small city right in the middle of the freeway. And so the thing about good representations, either in your mind or brain or in the world, is that they preserve functionally relevant information. They give you things that you can use. And so, for instance, you might keep in your mind's eye the distance between cities and how to get from one city to the other. And so you might say, well, okay, here I am in La Jolla, and maybe I want to go to Del Mar. So, this is not La Jolla, this is not Del Mar, sorry. Here I am in, I'm in East San Diego, sort of near El Cajon, but I want to go to La Mesa, so I got to get in the car and go that way. You might and it's what? It's maybe 5 or 10 miles away. Or I might just throw out instructions. But either way, the distance between cities, or how to get from one city to the other, is maintained in your representation. And there are two distinct ways to represent spatial information that preserve functionally relevant information. These are the analog and the propositional approaches, which I've been talking about. So analogical. Analog is almost like a picture in the head, and propositional, which is more based on instructions. So with analogical perception, imagery is like perception. You know, we walk around, we have these pictures. You know, we have depth cues. We have a sense of depth and, you know, expansion and direction. So maybe there's like a picture in our head. Images retain some of the sensory qualities of perception. So I close my eyes and I think back and I think of my grandmother who died in the 70s. And I can still see the color of her skin. I can see the color of her hair. I can see the chair she's sitting in. So the thing is that image seems, at least in my mind's eye, to have some of the sensory qualities of perception. As opposed to propositional. They're like descriptions of visual scenes. All right. So if I might be looking at a picture, and I'll tell you about it. I'm looking at a picture of my grandfather's house, and on the right there's a tree, and on the left there's his car. And so I'm making lists of things that are in the picture. And you're not actually looking at the picture, but you're sitting there recording all the things I'm saying. And so it's a set of descriptions as opposed to the cues themselves. And that's a propositional representation. And so it's like the memory model from Chapter 5 in some ways. You've got items stored. You know, it's like the semantic networks of meaning. And so you can think about this is going to give you an example of this. This is one of the less interesting figures I'm going to show you, but it's going to make sense. In an analog representation, there's more or less direct relationship between representation and referent. So I'm looking here. So this is maybe what's showing up on my screen of consciousness and on my visual spatial sketch pad. So I've got a map of 6 cities, cities A, B, C, D, E, and F. And even though it's not the same, it's like a map in the sense that there's a direct relationship between the true distance between cities and the distance between cities on the map. So it may be that an inch here is equal to a mile in physical reality. And so the map is like a picture in the head. It's even though it's not the place itself, even though it's not the terrain, you can look at it and you can do things with it. Spatial relationships are also captured. So if you look at this, you know that F is to the north of E, and that E is to the east of D. You can just you can play around with this image if you put it in your head, and you can do things. Okay, I want to get to city F. I may not know exactly how to get there, but I know I have to drive in that direction. Analog representation. At the same time, some information is hard to get. Exactly how far apart are F and B? Well, you actually have to record that. I mean, you might be able to picture, oh, it's a long way, but how do you know how far apart F and B are? You have to actually make a list. And so this sort of information isn't captured well in analog representation. As opposed to propositional representation, where F is maybe a reference. You can say F. If I know I'm standing at F, I know that E is 10 miles south. I know that, these are just lists. I may have in my mind the D is 10 miles south and 30 miles west. So I have all these instructions here. But so with the propositional representation, distance and spatial information are preserved like analog. But unlike the analog, some information is easy to get and some is hard to get. So how far is B from F? How do you go from B to F? Well, that's easy. You just sort of make a set of instructions, and you've already recorded in your mental list what the distance is. But it's hard to say how close are B and D. You somehow got to do some other manipulation. Is this ringing more true for the way that you organize the world? You're a prop. How about you make lists, right, of directions, or you can kind of do both. Okay. But this is making sense. You'll make when you're driving to a new place, you want the MapQuest instructions or whatever, or you want the GPS to tell you when to turn right or turn left. But just the map saying turn left here, go 3 miles at this exit, get off, right? And you've argued with people over directions a few times because they're doing something totally different and weird. Right? Yeah. Okay. You can admit to it. And then the rest of you, it's amazing to me. This is what's happening. It's a generational shift, I think. The rest of you all just look at pictures and say, most of us do both, but some of you are more leaning toward, okay, I know where I'm going. I'm driving. So how many of you would actually consider yourself more of the analog type? The pictures in the head type. How many of you are more the propositional type? Just out of curiosity. And by the way, what's interesting is that people tend to find each other. You have analog and propositional in the same relationship fighting with each other, which is probably a good thing. Okay, anyway. I just find it amazing. But back to the science. So we've got these two types of representation. And I want to skip down. Let's see. Also 7. Okay, so there's all the stuff you can do. You can have root information here. And so you've got, in the propositional representation, you have distance and spatial information preserved, but some information is easy to get and some is hard. It's different than in the analog representation. So it's easy. How do you get from A to B? You just picture it. But if you have to drive through B to get to C, get from A to C, it's a little bit harder. So it's different representations, analog and propositional, but they allow access to certain information more readily than the other approach. So analog and propositional representations both have their advantage. Most of us are wired for both, really. So let's just go down some of the things that happen here. So you've got the analogical, more picture in the head like, again, it's not completely like a picture in the head, versus the propositional, which is more like the list, or we'll call them propositions. So when we go to analogical, visual memory is stored using like a picture-like code, as opposed to propositional. Visual memory is stored using a word-like code, a list of instructions, words. In analogical, visual memory is like perception. If I think about my grandmother, I call it kind of an image, a picture of her. It's interesting. Some people have no capacity for faces. Other people don't. But if I have that capacity, I call this image of, I can see my grandmother standing there. As opposed to visual memory and propositional is like a description of the image. So maybe I remember that my grandmother had age spots and gray hair and a certain way of sitting in her chair, and she was really nice and sweet. But I'm listing stuff. I'm not actually looking at her picture. I'm listing the propositional reality. So it's like a description. So very different. Then we have relations are represented implicitly in analogical representation. In other words, it's like I'm looking at a picture. Whereas in propositional representation, it's explicit. I live 10 miles from SDSU. I have to go on to the 8, get off at college, and drive up to campus if I want to get to SDSU. Explicit. And finally, there's a different kind of representation for each sense in analogical representation. I can have auditory imagery. I can have visual imagery. I can even have nasal imagery, touch imagery. I can imagine holding a basketball in my hands, and I can kind of imagine the sphere and the feel of the basketball. That's a visual and tactile representation. So I can have, whereas if I'm doing it propositionally, it's different. Nope. I can't really imagine the basketball, but I can say, well, it's got bumps on it. It's got lines on it. It's yellow, or I'm sorry, it's orange, whatever. I don't know. It's like the old ABA. It's red, white, and blue. But so I can kind of make lists, but they're very different. And most of us have a capacity for both, and in different amounts. And so, but for years, people wanted to know which was it. For years, people didn't believe in the whole notion of analog. And people like Roger Shepard and Stephen Kosslyn, these are both names you want to know, Kosslyn, came along and showed that, in fact, there had to be at least this is how most of us interpret it, there had to be an analog representation in addition to a propositional one. And so, okay, what do I hear? So is the nature of mental imagery analog or propositional? It could arise from either. All necessary information is present in either. One side, there still are people out there who argue that all knowledge is propositional or list-based. Propositional representations are so powerful that you don't need analog representations. And so they say, why have two types of representation when one will do? And the other side, which involves people like Shepard and Koslin, argue that analog representation is more efficient for spatial knowledge, that there's good reason to have both ways of processing information. Precisely because propositional representations are so general, they aren't well tailored to special needs, like representing spatial information. So even though it's nice to make a list of places to go, sometimes you just need to make up an image and manipulate it. And so where's the evidence? How are we doing here? So I come back to this study I showed you at the beginning of this lecture. The evidence for mental rotation provides strong evidence for analog processing. And really in the 70s and 80s this was huge, because all of a sudden it made it harder for these people who were not interested in mental imagery to function. And so all of a sudden you had this science of the subjective that was developed beautifully. So I've already shown you how this works, so I'm not going to necessarily go through all the details again. You get a couple objects and you ask if one is simply a rotation of the other. This is the same slide I showed you before. And I mentioned before the representation seems to correspond in direct ways to the objects themselves, which is what you'd expect with analog but not propositional representation. So most of us can form this picture of one thing in our head and see if it rotates into the place of the other. And a few people do what people thought everybody used to do, which is you're trying to kind of make lists and count things and trying to see if things can logically add up, right? So the fact that you get this linear response, the fact that more degrees of rotation means longer reaction time, huge finding, because it suggests that in fact you do have a picture in your head and you are truly mentally rotating it. And for those of you who have a hard time with image capacity, this is what we think is going on. Let me do this again. So watch. This is what we think is going on in the head to match these. When I say same or different, it's like you're doing this in your mind. You're moving the piece around to see if they actually fit. Well, they did more studies, and this is another simple one. You can have, for instance, the letter R. You can have a normal letter R or a backward letter R, and they can be rotated in various positions. So you can take the letter R, you can rotate it 300 degrees, 240 degrees, 180 degrees, or you can do it backwards, so you have an inverted or a mirror image of the R. You can do the same thing, and you can say, all right, are you looking at a mirror image of the R, the real R itself? And obviously when it's upside down it's hard to know. You have to actually kind of flip it over in your mind's eye. Well, it turns out again that it's pretty linear. The more degrees of rotation, the longer it takes. And so again, this was taken as evidence for mental rotation. So it takes longer. The reaction time increases the more rotated it is. And so with mental rotation studies, most people agree, not everybody, but most people agree that this provides evidence for an analog representation in addition to a propositional representation. Some controversy remains. There are still people out there who would like to argue that there's no actual real imagery, but these people are a sort of shrinking minority, especially now that we're finding areas of the brain that actually seem to be involved in representing images and maps. Well, another line of evidence, and I think this is where I'm going to just talk a little bit about this line of evidence, and then we'll call it a day. Image scanning. Image scanning. And this is Steve Koslin. We're going to be revisiting Dr. Koslin. But here's Steve Koslin. And he's looking at a brain right there, and he's kind of a fun, interesting, weird guy. He's at Harvard, And he's done some classic studies of mental imagery. Now, just to give you a sense of how this works, imagine you're a victim in this study, a subject, 1978, and you look at this map of an island, and there are 7 locations marked on it by objects. You've got an X up here, you have grasses over here, you have a tree over here, you have a lake, you have a hut, and you have a water well right here. And I just say, okay, I want you to look at this and form it. Just keep looking at it and memorize the picture. Form an image in your head of what you're looking at. And you do that for a while. Okay, and then I have you close your eyes. In fact, I want you. So you can try this. Close your eyes. And well, actually, don't do that. No, open your eyes. But so I have you close your eyes, and imagine you're closing the eyes and you're imagining the entire map. So maybe I have you in your mind's eye. Actually, close your eyes. In your mind's eye, I want you standing at the hut at the bottom. So close your eyes. Stand at the hut at the bottom. And I can ask you, was there a lake on the map? How many people say yes? Good. And then I ask you, was there an X on the map? Were there grasses on the map? Yeah. Anyway, so you get the basic picture. And so the point is if you do this, I could have you do this, and I could measure your reaction time to answer these questions. And you respond as quickly and accurately as you can. What they find is that your reaction time, actually I think that's on the next slide, your reaction time is related to the distance on the map. So you close your eyes and you fix this image in your head. Longer distances take longer to scan. In other words, if you're standing at the hut, you can answer on average very quickly that there's a lake. But it takes you a whole lot longer to tell you that there's an X or that there's grasses. And this is some of the data from the original study, and these are averaged over lots of subjects and lots of trials. But this is distance in centimeters on the map, and this is time that it takes to respond. The farther away on the map it is, so I have you stand in a particular place on the map and tell you whether there are objects. It's a linear response. It's almost like you're scanning a map in your mind's eye, and it takes longer to scan longer distances. Now, nobody knew this, and yet the reaction times indicate that we have to scan the images. Okay, one more image scaling demo. You form an image of an elephant, and you form an image of a rabbit next to it. So go ahead, do that in your mind's eye. You have an image of an elephant, and next to it is a rabbit. And then I could ask you, does the rabbit have a pink nose? And it takes you a while to respond. How many people's rabbit has a pink nose? Okay, and how many people doesn't? Okay. Now we're doing the second, and we do this counterbalanced and all like that. We make sure that we did this scientifically in a way that randomized key variables. But now I have you form an image of a rabbit and form an image of a fly next to it. Now I ask you, does the rabbit have a pink nose? And it takes you a while to respond, and you respond. Well, okay. When he did this study, if he had you do an image of an elephant and a rabbit, people were slow to tell you whether the rabbit had a pink nose. Relatively slow. It takes you a while to zoom. You've got this giant elephant and this tiny rabbit, and the idea is that, well, you've got to kind of zoom in on that picture of that little rabbit to see what its nose looks like. Whereas if you have a rabbit and a fly occupying your mental imagery space, all of a sudden the rabbit is huge compared to the fly. And so you don't have to zoom in. And what Koslin found was that when he measured reaction times, if you had the elephant and the rabbit, people were relatively slow to answer the question. If you had the rabbit and the fly, they were relatively quick, suggesting that people are in fact scanning images. And he did a bunch of experiments like this. So this kind of shows you. Let's see, yeah. So people answer questions about large images faster than about small images. And again, this is evidence to suggest that there's an analog representation. Okay. Well, where we left things last time is we were talking about mental imagery. And I hope it's obvious to you that mental imagery is something that I'm very fond of. So I'm going to finish up mental imagery. There's not much more to go, but I want to show you a few things, and I also want to show you some videos of Steve Koslin and related work. And then we'll move on to categorization, which I think is also kind of a fun topic. As I mentioned before, we're going to stop a little bit early today. The NCAA did not consult with me regarding their schedule, which is a little bit frustrating. I mean, come on. You want to watch the basketball game instead of come to class? I don't understand. But it's okay. It's all right. We still have a pretty good turnout today. Now, are the people here, how many people actually care about this game? Most people. How many people don't care? So it's actually pretty even. Okay. Well, so we'll be out of here in time for you to get to your local TV set. Anyway, so we've been talking about images and, you know, essentially establishing that in some ways it's like a picture in the head and in some ways it's not, this imagery thing. And there's been this long-standing battle. Some people saying, look, you don't need imagery. It's like it's either a verbal code of some form, but you don't actually need to form anything resembling a picture. And then at the same time, you have people like Shepard and Koslin and showing that in some ways, given how we study this, it almost has to be picture-like, although it's not exactly a picture. And so last time I showed you some classic experiments by Koslin, and so this time I want to start with a few video components. One talking about Koslin's research, and then a couple videos of Koslin actually talking about how he did these studies. And in some ways it's a little bit redundant with what we talked about last time, although I think the fact that it's sort of, you'll actually see Koslin talking about it and you'll actually see videos, I think it's going to help you remember this material better. And so, and maybe help bring it to life. And so the first thing I want to show you is from the Discovering Psychology series. Now if you look at the syllabus, I actually listed for some weeks there are Discovering Psychology videos I wanted you to watch. If you go to Google Video and you type in Discovering Psychology Cognitive Processes, you'll find this video. And there's just a small portion on imagery, and there's a bigger portion on categorization that I think you'll enjoy watching. So for starters, let me just start, and I want you to see, you're going to see Philip Zimbardo talking about Koslin's work.
Moreover, when new information clashes with an established schema, there's a violation of our expectations, and our mind reacts instantly. Just compare your reaction to this sentence to this one. This violation of your expectations is detected instantly by your brain even before you're consciously aware of it. Now, sometimes we don't have enough information to activate the right schema until we add the right cue. And sometimes we activate the wrong schema entirely. Take a good look at this drawing. It's an example of how our interpretation of new information can become faulty or biased. Try to remember the image you just saw. What do you think was happening there? For a number of research subjects, the knife was perceived to be in the hands of the black man. These subjects reconstructed the information found in the picture around their own biased schemas, which blacks are always seen as the aggressors. And so the knife changed hands in their mind from the white aggressor to the innocent black man. Here's another way we go wrong. Which is farther north, Seattle or Montreal? And which is farther west, the entrance to the Panama Canal on the Pacific Ocean side or the entrance on the Atlantic side? In fact, Seattle is further north, but we usually think it's Montreal because we picture Canada as always being north of the U.S. And it's the Atlantic entrance of the canal that's further west, despite our assumption that the Pacific is always west of the Atlantic. What's happened is that we've been led astray by the mental maps we have in our minds. These maps can enlarge nearby familiar places and foreshorten faraway places, like this satirical picture of the world from a Bostonian's perspective. We also store mental pictures of objects like this one and scan them in our minds in much the same way we scan actual objects with our eyes. Now think back to the picture of the motorboat. Did it have a windshield? Did it have an anchor? When researcher Steve Coslin asked subjects each of these questions, they tried to answer as fast as they could by pressing a button. Results indicated that it took them longer to remember that there was an anchor than a windshield. This longer reaction time was taken to mean that the subjects were scanning a visual image of the motorboat in their minds. And because the anchor was farther away than the windshield, when they scanned the image starting from the back of the boat, it took longer to see the anchor with the mind's eye. A similar result occurred when subjects were asked whether each of these letters was a normal R or a mirror image. The further the R had been rotated, the longer it took subjects to answer, because in their minds they had to rotate the R's back into an upright position. Unlike computers, we humans often process information inefficiently. When subjects are asked to plan a shopping trip, for instance, they do so by skipping back and forth. That's because instead of reasoning out the problem in a direct, linear way, we tend to process information according to the meaning it has for us.
Okay. Oops.
If you like going...
And so, the key thing from there was a lot about imagery. You got to see Shepard's classic experiment with the rotating R's. In other words, one of his classic mental rotation experiments. And you got to see one of Coslin's classic experiments. Now, I've shown you other scanning experiments, for instance, with an island, or with a rabbit versus an elephant versus a fly. But in this particular case, it was a case of the motorboat, and scanning the image of the motorboat and showing essentially that it is, in many ways, like a picture. Now, I think one of the things that I have to tell all of you, you come from a very visual generation. You know, you're on the internet, you are bombarded with images in the media, on the internet. You're a visual generation. But if you go back several generations when this work was being done, people didn't necessarily see the world the same way. They didn't necessarily realize just how visually active we are. And so there was this long-standing debate about whether or not you could actually form something like an image. And we call this the analog representation, if you remember from last time. An image-like, a perception-like representation. And so it was these studies that caused a lot of people to wake up and say, oh yeah, it isn't just propositional representation. And there was a long-standing, there's still a debate, but I think most people now would buy, based on these evidences, and also evidence from the brain, that we are analog processors as well as propositional processors. Now, I'd also like to show you a video of Steve Coslin actually talking about some of this. And this is a lecture he is at Harvard, and he's going to talk a little bit about his methods and the behavioral studies that went into scanning. Now, if you want to watch the rest of this, so if you go and you Google Harvard lecture, the state of cognitive neuroscience, P1, part 1, and you go about 6 or 7 minutes in, you can hear this lecture again. And this is Steve Coslin talking about the experiments that he did to establish imagery, and especially analog representation as something real. So talking about the logic of his scanning experiments.
So how do you try to demonstrate that when you have the experience of a mental image, there's a representation underlying it that looks like that, okay, that has those kind of properties? So the alternative is it's all kind of language-like, and the experience is epiphenomenal. It's like the heat from a light bulb when you're reading. The heat plays no role in the reading process. people have claimed that the experience is entirely epiphenomenal, that all mental work is done with a single language of thought that's essentially language-like. So the issue is there more than one language of thought? Are there at least two, one of which is depictive, which uses a different kind of form of representation as opposed to linguistic? Clearly there's linguistic representation. So, first set of experiments that at least I did used behavioral methods that used response times and error rates as a way to try to externalize what was inside the head. So here's one experiment. Try this, actually. Close your eyes. Imagine Snoopy the dog and focus your mental gaze on his feet. Can you do that? Okay, now tell me whether his ears stick up or they hang down. Okay? Well, if I had measured the time to make that decision, you would have taken more time than if I'd asked you to start off focusing on the center of his body, and that would have taken more time than if I'd asked you to start off focusing on his head. The further you shifted your mental gaze from where you started, his feet, middle of the body, or head, to the target, the ears, the longer it would have taken. So we've done experiments to demonstrate that more formally. Here's one. This is an island with 7 locations on it that are positioned such that the 21 interpoint distances are all distinct. People learn to draw this map, indicate the hut with that X, the well with that X, and so forth. They get very good at doing this. Later, they close their eyes. They hear the name of one of the locations, like hut. They're asked to mentally focus their gaze on that location, wait, their eyes are closed, and then they hear the name of another location, another object, rather. It could be tree, could be grass, or could be bench, which is not on the map. Their job is to look for, quote unquote, the second location. If they find it, push one button. If they looked around and can't find it, push another button. Measure response time. So we have them start off focusing on each object equally often, and they end up on each other object equally often, and then of course an equal number of cases where they didn't find it. These are response times as defined as a function of the distance between where they started initially and where they ended up. So what you see is the further they have to scan, the longer it's taking. That's just what you predict if in fact there's a depictive representation there, which there's some kind of mental space being used to represent actual space. So we're using response times as a kind of mental tape measure. The further they have to scan, the longer it takes, which presumably is evidence that there really was distance embodied in the image. We've done this without using any imagery instructions. So here's a task where they see an annulus, a square annulus. There's 3 cells that are filled in randomly. They study this, push a button, it goes off, and then an arrow appears for 15 milliseconds. The arrow can be anywhere in this interior region. 3 distances, this is far, here would be medium, that would be close. The task is simply, if it were present, the entire display the way you're seeing it now, would the arrow point to a filled square, as it does now, or an empty square? And it's a good imagery task. It's based on something that Steve Pinker and Ron Fink invented years before. It doesn't require any instructions to use imagery. What you find is the times, near, medium, and far, increase with distance. This is Harvard students, by the way, and these are Air Force pilots. E.T.L. Dror and I did this experiment years ago. He actually lived on an Air Force base for a summer to test the pilots. And what you see here is the slopes are identical. That is the time to scan. But the pilots are just generally faster. Just as an aside, mental rotation. So try this. Imagine the uppercase letter N. Can you do that? If you rotate it 90 degrees clockwise, is it another letter? What is it? Okay, well, it turns out the further you have to rotate, the longer it takes. Roger Shepard had demonstrated this years ago.
Okay. You get the basic idea. And so this is all redundant with what we talked about last time. And yet I think it does a nice job of, again, clarifying and stating much of what is central to this notion of image scanning. And again, I want to emphasize to you that maybe in 2010 this seems almost obvious, and yet for many years it wasn't. And it shows us about our visual nature. Now, I'd be very curious at some point to look at the individual differences in this. So those of you who don't identify as being sort of image processors, it'd be interesting to try some of this on you relative to the rest of us, because these are average results. But what about individuals? If you're not very good at processing images, if you identify as that, are you going to be worse at these? Are you going to show something that doesn't make sense in terms of what Costlin is suggesting for the group? I'm not sure that that question's been answered yet. Okay, so where's my PowerPoint? There it is. Now we'll talk about imagery in the brain in just a few seconds. But so we leave image scanning, and now we take on this notion of pictures in the head. Because in many ways, the research I've been showing you has been suggesting that in many ways we create this three-dimensional object in our mind's eye that in many ways is analogous, remember analog, analogous to the actual object itself. And that we operate upon this internal representation like a three-dimensional image of the object. But let's talk about some of the limitations of this, both and some other details of this. So once again, we've already met Steve Koslin. He's from Harvard. He's a psychologist, and he's also a cognitive neuroscientist, one of the first and best of our generation. And he did those classic studies of mental imagery. We've already talked about this, so I'm going to move on. So we're moving into this notion of pictures in the head, reinterpreting mental images. And again, so this is going to lead in for the next video. Visual areas in the brain are active during imagery. And so once again, Koslin, having done all his behavioral and cognitive studies, then went into the brain. He, as he came of age over the last 30 years, 20 years, the techniques for looking into the brain, whether it's PET scan or fMRI, these things developed considerably. And so he was able to look, and one of the questions he was interested in is, well, given that he was hypothesizing that imagery is in many ways like vision, he wanted to find out how many areas the visual system shared with imagery. And so this is what happened. And so this leads us to my third video of the day. And this is the Discovering Psychology Series 25. And if you go about, let's see, it's almost 10 minutes into the video, you'll find Steve Koslin, and this is what he has to say.
It is known that the cortex is very plastic and organizes itself around the experiences it has. So maybe simply because we look at faces all the time in our daily lives, that is sufficient to produce a special purpose patch of cortex that does face recognition. But of course the other perfectly plausible story is recognizing faces.
Stephen Koslin of Harvard University. Researchers have now discovered that many of the brain areas used for vision are also the same as those used while we imagine. Stephen Koslin of Harvard University has been investigating the relationship between these two complementary visual systems.
It wouldn't be a pity to let 40% of your brain just be involved in perception. Why not usurp that, use it in thinking as well? And that's what mental imagery is all about.
Mental imagery allows us to manipulate what we have stored in visual memory, so we can use that information to anticipate and solve problems.
Yeah, this sort of looks like an oxygen mask, but it's...
With another brain imaging technology, PET scan, Koslin's team has studied how visual perception and mental imagery overlap. On a computer screen, subjects imagined the letter inside a grid. An X was displayed. The subjects had to indicate if the X touched the imagined letter. Finally, they identified objects displayed at oblique angles. Of all the brain areas active in mental imagery and in vision, 2/3 were activated in common. We quite literally see with our mind's eye. We even move our eyes in the same way while we imagine a scene as when we visually scan the scene in the external world. For example, think of your living room. As you do, you'll scan the walls looking for details, count the windows, even zoom in on objects in about the same amount of time as you would if you were actually viewing it.
When you generate an image, you're conjuring it up. Often you actually build up an image by putting parts on it. So you've got forming images, you've got image inspection, which can involve scanning around or zooming in, interpreting patterns and images, that holding on to images over time and image transformations, which include rotating, expanding, bending, various kinds of other things. Each of those abilities is carried out by a host of separate processes. We can piggyback on this enormously complicated system that helps us navigate in the world to also anticipate what we would do or to think about possibilities that don't exist currently.
Using fMRI, researchers have revealed how the brain is changed by what it experiences, how it is dynamic, never static.
Okay, so this is more evidence suggesting that in many ways, vision and imagery really, in many ways, go together. 2/3, I think it's a good number to remember, 2/3 of the areas subsumed by vision and imagery overlap. And you heard about that, you saw that in the video. So more evidence that these things are not unrelated. But then if we go down the rabbit hole a little bit deeper, we start running into a few snags and realizing that imagery isn't exactly the same as a picture in the head. So can you replicate visual illusions using mental imagery? And these I just listed several. The Ponzo illusion is where you have two lines going off into the horizon and then two cross lines that are the same length. And to answer this question, this is a duck and a rabbit. So if you look at that for a moment, if we look at this, how many people can see both images in this? How many people are still working on it? So all of you can look at this and reverse it between duck and rabbit. So I want you to now, who's still working on it? Okay, keep. So if it's what's that? Good. Yeah, the duck is looking this way. There's his beak. There's his eye. Versus the rabbit's looking this way. There's his nose, eyes, and there's his ears sticking back. Magic. We do magic tricks in here. No. So this is a classic reversible figure. And simple. So now, imagine the study that was done by Chambers and Riesberg in 1985, where they used this. And so they used the duck-rabbit ambiguous stimulus. And they took 15 subjects, and all of them could look at this and reverse back and forth between the duck and the rabbit. But they couldn't do it when they actually took the mental image. So imagine I show you this for the first time, and I don't tell you it's a reversible figure. I just have you tell me what you see, and some people say I see a duck, and some people say I see a rabbit, and I have you then memorize it. So you memorize it, and then I take the picture away, and then I see if you can reinterpret it. And the fact is if you're just holding the image in your mind's eye as a rabbit, you can't make it reverse in your mental image. So whereas if we're actually looking at the picture, we can make it reverse back and forth. You can't do that in your mind's eye if you're holding the image. So this was some evidence to suggest that mental images aren't exactly like pictures. The fact that if you're actually just looking at them, you can reverse them. But if you're holding the image in your mind's eye, you're unable to reverse it between the duck and the rabbit. And yet you can then draw it. Let's see, I thought this was all in there. But if you then redraw the image you're holding in your memory, you can then look at it on the page and say, oh yeah, I see it's also a rabbit. Oh yeah, it's also a duck. And so this was interesting because it suggested that, okay, you can't do that sort of flipping back and forth with an ambiguous stimulus that you can do when you're actually looking at the image in real time. What's interesting, here's Steve Koslin and the Dalai Lama, who has gotten very interested in neuroscience these days. And so he and Koslin met. And so one of the questions is, are people who really put a lot of effort into, say, meditation and, imagery, contemplative practice, are they able to do these sorts of tasks? And these studies are ongoing. And so there's the Dalai Lama and Koslin and the duck-rabbit illusion. Now, let's see, what else? Oh yes, now there's actually a brewery called the Duck Rabbit Brewery. And you might all want to know this. I was trying to get a hold of some of this beer, and the whole label's based on this illusion. There's the Duck Rabbit, and you can buy their Duck Rabbit brew. There's a Duck Rabbit T-shirt. Come on, guys, this is good stuff. Come on, it's Thursday night. And just to prove to you how vigilant I was to try to get a hold of this, this is from a couple of years ago, about a year and a half ago. Dr. Peterzell, thanks very much for your interest in the Duck Rabbit Brewery. I wanted to get free T-shirts for my class. Didn't happen. As to T-shirts, we aren't set up for card transactions, but we're more than happy to accept checks. Currently, we have standard T-shirts in green and chestnut. Goes on. Let's see, what else? As to shipping beer to California, I mean, I wanted to get beer for my class as well, but we don't sell direct to the public at all. There is, however, a store in Asheville, North Carolina that ships out beer all over the place. Anyway, so if you're interested in the Duck Rabbit illusion, never mind. Okay, onward. Okay, so that has to do, so the take-home message in all of that is that something, ambiguous figures, while you can flip them in real time, if you put them in your mind's eye, you can't flip them the way you could in normal, visual processing. So let's talk about remembering details as well. Now, most of you, if you're from this culture, have spent your whole life looking at pennies. How many people have spent your whole life looking at pennies, or much of it? Only a few of you? Wait a minute. How many of you grew up looking at pennies? With pennies, spending pennies. So pennies have been in your life for many years. Can you picture the penny right now? You can kind of picture it in your mind's eye, Honest Abe there, looking all whatever. Okay, so now the question is, which of these is the real U.S. penny? Okay, so we're gonna look through here. Why don't you look through here for a moment and try to decide which of these is the real U.S. penny? And I'm gonna go through. I'm gonna give you 10 seconds, 15 seconds even, to just look through there and try to determine which is the real U.S. penny. Because you're so familiar with it, it should be easy. All right, so we're going to start the questionnaire now. How many people are still trying to figure it out? Okay, good. How many people say A, B, C, D, E, F, G, H, I, J, K, L, M, okay, we got one L, M, N, O. So people were pretty all over the map. So anybody not vote? Probably some of you didn't vote. Well, the point is, this is hard. Even though you've been looking at pennies your whole lives, you may remember the fact it's copper, it's got Abe Lincoln on it, it might say a couple things, but picking out the right one. Now, in fact, those of you who guessed A guessed properly. So you can see here are three versions of the U.S. penny, including the 1909 SVDB, the first year that they did this. We've been dealing with Lincoln pennies for 101 years, by the way. This is the penny that was made during World War II, not made out of copper, and this is the one that's more recent. And if you look at it, it all maps onto A. So the point is now in this particular case, I think only 4 or 5 of you got this right. Usually, when you do this, less than half of us get it right. And this was back in 1979 when the penny was actually worth a lot more than it is now. Now you're much less likely to look at it. You just drop it in that thing, give a penny, take a penny. I never take a penny. I always give the pennies. But the point is even though we can form most of us can form a fairly strong image of this highly familiar object, there are aspects of this object that we haven't encoded. And so it may feel like we're looking in our mind's eye at the penny, But when we have to make decisions about which of these is the real penny, it's not easy. It's difficult, and we make a mistake. And so, again, this points to not exactly a picture in the head, but something that's an analog where items are in there, but there are things missing. Much like a map, like a written map. The written map may not show all the trees and the mountains and the rocks, and yet it's a fairly reasonable image of the terrain you'll find. I'm not going to show this to you again. This is the failure to notice a changed person. Remember, when you walk through with a door, you separate two people. The guy who's giving directions doesn't necessarily even notice that a change has been made. And it's, again, related to this sort of topic. But I'm going to skip through the cognitive or the image distortions, and I want to mention cognitive maps since you saw it in the video. And wow, what's going on out there? Okay, so we have lots of knowledge about the spatial environment, and so most of us can kind of imagine and draw a map of our apartments, or our rooms, the contents, parts of campus, maybe even the United States. We can readily give and receive directions about environments we're familiar with, but when we look at these so-called cognitive maps, we can usually answer these questions, but we oftentimes answer them wrong. What's farther west, Los Angeles or Reno? Well, we tend to think of Los Angeles as being farther west because it's on the west coast, whereas Reno's inland. But in reality, Reno is actually farther west. So this is something other than perfect imagery. This is something about propositional representations kicking in. Which is farther south, Seattle or Montreal? As you heard, it's easy to think of Montreal as being north of the border in Canada and Seattle as being south of the border in the United States. But in reality, Seattle is further north than Montreal. It gets us in trouble. And we can do this with a number of other things like the Panama Canal, as you saw. And the second answer of these is correct in each case. And so there is some non-analog general knowledge that messes up our actual imagery. Okay, so that's all I had to say about imagery. And now I want to just, any questions before we move on? I see a question in the back. I'm sorry. Right, and that was ongoing when, I mean, this was probably a few years ago. I'm not sure. I think, I couldn't tell you what the results were because they haven't published them yet. I know they were looking at it, but, I mean, you can imagine what the hypothesis, I mean, it's hot off the presses. It's been out there. So you might hypothesize that meditators might be able to do things with images that the rest of us can't. They might have a highly powerful imaging capacity that surpasses. But as far as the actual evidence, I don't know. I just know that they were very interested in it. I don't know what they ultimately found. But this idea that you can take it all in with, contemplative practices is something I know that they want to look at. Next.
When you were talking about not being able to replicate illusions or ambiguous figures, does that change if you're very familiar with the ambiguous figure?
Well, then it sort of becomes impossible to test it. Although maybe there might be some neural correlate. But the thing is if you've seen it before and you know it's reversible, then it causes problems. Because then it's better if you've never seen it before. So if you're highly familiar with it, it's just I'm not sure how you would do the science. But if I show you something you've never seen before that's an ambiguous figure, then I can have you do all sorts of things with one interpretation. So for instance, if you've never seen the old lady, young lady, and you look at it and say, oh, I see an old lady, and then you can ask all sorts of questions about the old lady. Can you memorize the picture of the old lady? You may never switch it to the young lady. But the point is once you're familiar with it, then I can't really test, see what I mean? You have to be kind of naive about the other interpretation when you encode it, or you can't really do the study. But it's a great question. And actually, if I think about it, the way that we might eventually get to that is with brain imaging. There may be a sort of aha experience or switch that you can notice in the brain activity. But I don't think we're there yet. As far as I know, nobody's looked at it. Good question. Next question? Any other questions? Okay, so that's imagery. And before we leave it, I just want to say, I think one of the things that I'm so fond about this are the individual differences in this. We've already talked about this last time, the fact that there are some of us who are good with images and some of us who aren't.